So, here's something worth sitting with tonight. Right now, as you lie there are something like 10 billion atoms in your body. Each one of them is mostly empty space. The nucleus at the center of each atom is so small relative to the whole atom that if you blew a single atom up to the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. Everything else, the enormous region where the electrons exist, is essentially nothing. No solid material. No stuff. Just a cloud of probability, a smear of quantum possibility hovering around that tiny marble. And the solid world you feel beneath you, the mattress, the floor, the ground, none of that is solid in any simple physical sense either. It feels solid because the electron clouds of neighboring atoms push against each other through electromagnetic forces, because the rules of quantum mechanics forbid two electrons from ever occupying the same state, which means atoms push back when you try to compress them together. The thing you're lying on isn't holding you up because matter is packed tight. It's holding you up because of quantum mechanical rules governing subatomic particles that were only discovered in the last 100 years. And here's the thing that gets me every time I think about it. For most of human history, not just most, for virtually all of human history right up until about 1900, nobody knew any of this. Nobody suspected it. The best scientists in the world, the people who had built thermodynamics and optics and the entire edifice of classical physics, had no idea that the world worked this way at the small scale. And when the evidence started coming in, when the experiments started pointing at something deeply strange underneath the surface of ordinary reality, many of those scientists resisted it with everything they had. Some of the most brilliant people who ever lived spent decades refusing to believe what the data was telling them, and then spent more decades arguing furiously about what it meant, even after they finally had to accept that it was true. That argument, in a certain sense, hasn't completely ended. We still don't fully agree on what quantum mechanics means at its deepest level. We know how to use it. It is the most precisely tested theory in the history of science. It works with a reliability that is simply astonishing. But what it's actually telling us about the nature of reality, about what's going on between measurements, about whether there's a deeper layer underneath, those questions are still open and still genuinely contested. And that's what we're going to talk about tonight. The whole strange, beautiful, maddening story. From the first crack in the classical picture all the way to the machines being built right now, that harness quantum weirdness to compute things no ordinary computer could ever touch. We're going to go slowly. We're going to let each idea settle before the next one arrives. And I want to say at the outset that none of this requires any background in mathematics or physics. The math of quantum mechanics is genuinely challenging and genuinely important. But the ideas, the actual physical pictures that the math is pointing at, those are accessible to anyone who's willing to let go of some assumptions about how the world works. Assumptions that feel so natural, so obviously true, that you've probably never thought to question them. Things like, objects have definite positions. Properties exist independently of whether anyone is measuring them. The same cause always produces the same effect. All of those things turn out to be wrong at the quantum scale. Not approximately wrong. Wrong in a way that is deep and strange, and has been verified to extraordinary precision. Let's start where the story actually starts, which is at the very end of the 19th century. Because the atmosphere in physics at that time is important context. There was a mood, particularly among the older generation of physicists, that the grand project of understanding nature was essentially complete. Newton had given the world mechanics and gravity. Maxwell had unified electricity and magnetism into a single set of equations of breathtaking elegance. Thermodynamics was thoroughly understood. The periodic table was nearly full. There was a sense among many people that what remained to be done in physics was refinement rather than discovery. More decimal places on existing measurements, filling in a few remaining gaps. The architecture, as it were, was finished. They were putting in the furniture. That confidence is almost funny in retrospect, because the edifice was already cracked. There were a handful of experimental results that didn't fit, stubborn anomalies that refused to be explained by classical physics, no matter how cleverly you tried. And one of the most persistent and most annoying of those anomalies had to do with something that seemed, on its surface, completely munda.
Classical explanation, and the quanta would turn out to be an artifact of a calculation, not a feature of reality. He spent years trying to find a way to recover his formula without the quantum assumption, and he never could. He described introducing the quantum as an act of desperation, a last resort after everything else had failed. And he remained uneasy with it for the rest of his career, which lasted a long time. He died in 1947 at the age of 89. He never fully made his peace with what his own calculation had started. So that's December 1900. Planck presents his quantum hypothesis to the German Physical Society. Physics has changed forever, and almost nobody knows it yet. Planck thinks he's applied a mathematical bandage to a bruised theory. What he's actually done is lit the first match on a revolution that will spend the next quarter century consuming everything around it. The person who picks up that match and runs with it is, of course, Albert Einstein. But not the Einstein most people picture. In 1905, Einstein is 26 years old. He has just completed his doctoral degree. He cannot get an academic position. He is working as a patent clerk in Bern, Switzerland. Third-class technical expert, which is the kind of title that belongs on a list of great historical ironies. During the day he reviews applications for patents. In the evenings and on weekends he does physics. And in that single year, 1905, working from a rented apartment in Bern, he publishes 4 papers, each of which would have secured a lasting reputation on its own. One of them is on special relativity. One explains Brownian motion, the erratic jittering of tiny particles in liquid, in a way that provided decisive evidence that atoms are real physical objects rather than mathematical conveniences. And the fourth, the one most directly relevant to our story tonight, is the paper that eventually won him the Nobel Prize. It's about the photoelectric effect. Here's what was puzzling. When you shine light on certain metal surfaces, electrons pop off. That's the photoelectric effect, and it had been observed experimentally since 1887. Now, classical physics says light is a wave. Maxwell had established that beautifully. And if light is a wave, like an ocean wave rolling into shore, then brighter light means a bigger, more energetic wave. You'd expect that crank up the brightness and you get electrons flying off with more energy. More intense light, faster electrons. That's the intuitive prediction. But that's not what the experiments showed. The energy of the ejected electrons depended on the color of the light, not the brightness. Use violet light, even dim violet light, and you get energetic electrons. Use bright red light, as bright as you like, and you might get no electrons at all. Brightness only affects how many electrons come off, not how much energy each one carries. Classical wave theory had no explanation for this. None at all. Einstein's explanation was radical in its simplicity. He said Planck was too cautious. Planck had quantized the oscillators in the walls of a hot object, the little mechanisms that emit and absorb energy. But Einstein said the quantization goes deeper than that. Light itself, traveling through space, consists of discrete packets of energy. Each packet carries an energy equal to Planck's constant multiplied by the frequency of the light. We now call these packets photons, though that word wasn't coined until 1926. But in 1905 Einstein described the reality: light is not a smooth continuous wave. At the level of individual interactions, it's a stream of particles, each one carrying a fixed quantum of energy determined by its color. Violet light has higher frequency than red, so each violet photon carries more energy than each red photon. When a photon hits an electron in a metal, it's a one-to-one collision. One photon, one electron. If the photon carries enough energy to knock the electron free of the metal's grip, the electron escapes. If it doesn't, nothing happens, regardless of how many photons you throw at it. A million gentle taps will never do what one firm knock can. This was a more radical claim than Planck's. Planck had quantized the machinery. Einstein had quantized light itself. And even Planck was skeptical. In 1913, Planck wrote a letter recommending Einstein for membership in the Prussian Academy of Sciences, which is one of the most prestigious endorsements a physicist of that era could receive. He praised Einstein in glowing terms, and then added, almost apologetically, that Einstein had sometimes overshot the mark in his speculations, citing the light quantum hypothesis as an example. Planck was essentially saying, brilliant man, but probably wrong about the photons. He was not wrong about the photons. And now you have something genuinely puzzling sitting right in the middle of physics. Light is a wave. That's not a guess. It's backed by a century and a half of experimental confirmation. Thomas Young's double-slit experiment in 1801 showed that light produces interference patterns, bright and dark fringes that appear only when waves overlap and reinforce or cancel each other. Maxwell's equations describe light as oscillating electric and magnetic fields propagating through space. Diffraction, polarization, interference, all of these wave behaviors had been observed and measured countless times. The evidence for light being a wave is overwhelming. And yet Einstein had just shown, and the photoelectric effect confirmed, that light also behaves like a particle. That it comes in discrete chunks. That it interacts with electrons one at a time. Both of these things are true simultaneously. Light is a wave and light is a particle. They are not compatible descriptions in classical physics. They seem to contradict each other, and yet the universe insists on both. This is wave-particle duality, and it's the first deep strangeness of quantum physics. When you first encounter it, there's an almost irresistible urge to assume that someone is being imprecise, that the physicists are using loose language, that really light is one thing or the other, and the apparent contradiction dissolves if you look carefully enough. It doesn't dissolve. The contradiction is real. The universe genuinely insists on both descriptions simultaneously. And the discomfort you feel trying to picture that, trying to construct a mental image of something that is both a wave and a particle at once, is the same discomfort the greatest minds of the early 20th century felt. Niels Bohr, who we'll spend considerable time with shortly, eventually concluded that you simply cannot ask what light really is between measurements. The question doesn't have an answer in any physical sense. What you can say is what light does when you measure it in a particular way. Ask a wave question, get a wave answer. Ask a particle question, get a particle answer. But there is no single coherent picture of what light is in itself, independently of any measurement. That conclusion offended many people deeply. It still does. But as of 2025, it has never been successfully challenged. Let's stay with the state of physics in the early 1910s, because alongside the light quantum puzzle, there's another crisis brewing. It concerns the inside of the atom, which nobody had gotten a clear look at yet. The electron had been discovered in 1897 by J.J. Thomson at Cambridge, who showed that cathode rays were streams of negatively charged particles far lighter than any atom. Thomson proposed a model of the atom as a diffuse sphere of positive charge with electrons embedded in it like raisins in a pudding. It was a reasonable first guess. And then in 1909, in a laboratory in Manchester under the direction of a large, loud, relentlessly energetic New Zealand physicist named Ernest Rutherford, an experiment was set up that demolished it completely. Rutherford had his assistants Hans Geiger and Ernest Marston firing tiny positively charged particles, alpha particles, at an extremely thin sheet of gold foil. The alpha particles were like tiny fast bullets, helium nuclei moving at a significant fraction of the speed of light. If Thomson's plum pudding model were right, the positive charge in the gold atoms would be diffuse and spread out, and the alpha particles would punch straight through with only minor deflections, like bullets through fog. And indeed, most of them did exactly that. They passed through the foil as if it weren't there. But some didn't. Some deflected at large angles. And a small number, a tiny, astonishing fraction, bounced almost directly backward. Rutherford later described his reaction by saying it was as if you had fired a 15-inch artillery shell at tissue paper and it had come back and hit you. He meant that almost literally. There was only one way to explain those backward scattered particles. Almost all of the mass of the atom and all of its positive charge had to be concentrated in a fantastically tiny region at the center. A region so small that the vast majority of alpha particles never came near it and sailed through unimpeded. But the rare particles that happened to fly directly toward that tiny dense center were violently repelled, deflected at large angles or bounced straight back. Rutherford called this tiny central structure the nucleus. The numbers were staggering in their implications. If you enlarged a single atom to the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. Everything else, the enormous space the electrons inhabit, is essentially empty. The solid world is almost entirely nothing. Rutherford published his nuclear model in 1911, and it was immediately compelling because it explained the scattering data beautifully. But it came with a problem. A devastating, apparently fatal problem. Because classical electromagnetism is very clear about what happens to a charged particle moving in a curved path. It radiates energy. Any accelerating charge emits electromagnetic radiation. And an electron moving in an orbit around a nucleus is accelerating, because circular or elliptical motion is accelerated motion even at constant speed. The direction of the velocity changes continuously, and changing direction is acceleration. So a classically orbiting electron should be continuously emitting electromagnetic radiation, losing energy, spiraling inward toward the nucleus as it loses energy, getting faster and radiating more as it spirals tighter. And the time for this to happen is not slow. The calculation gives something like 10 to the minus 8 seconds, 100 millionth of a second, for the electron to spiral all the way in and the atom to collapse. Every atom in the universe, according to classical physics, should destroy itself almost instantly. Clearly they don't. You exist. The universe exists. Chemistry works. Something is profoundly wrong with the classical picture of orbiting electrons. This is the second crisis that only quantum mechanics can resolve. And this is where Niels Bohr enters the story, and he deserves a full, slow introduction because he is one of the most fascinating and ultimately most important figures in this whole saga. Bohr was born in Copenhagen in 1885 into a household where ideas mattered enormously. His father was a physiology professor and a man of wide intellectual interests. His mother came from a prominent and cultured family. Niels and his younger brother Harold grew up in an environment of serious, passionate conversation about science, philosophy, literature. Harold became a distinguished mathematician and, in a detail that somehow fits perfectly, an Olympic silver medalist in football for the Danish national team in the 1908 Olympics. Niels was quieter, more intense, more prone to thinking slowly and deeply. He had a way of working through problems from every possible angle before committing to a conclusion, and his conclusions, when they arrived, tended to be revolutionary. He also had a legendary way of expressing himself, so careful, so hedged, so full of qualifications, that people sometimes genuinely couldn't tell what position he was taking. There are stories, probably embellished but grounded in truth, of physicists leaving Bohr's lectures uncertain whether he had claimed anything at all. In 1911, Bohr completed his doctorate in Copenhagen and went to England. He spent a short and not particularly fruitful period at Cambridge with J.J. Thomson, who had discovered the electron and had his own ideas about atomic structure and was not particularly receptive to a 25-year-old Dane questioning them. Then Bohr moved to Manchester to work with Rutherford, whose nuclear model was fresh and whose laboratory was one of the most exciting places in physics at that moment. And confronted with the instability problem, the fact that classical physics said Rutherford's atom couldn't exist, Bohr did something that took a particular kind of intellectual courage. He didn't look for a classical solution. He didn't try to patch Maxwell's equations or find some subtle mechanism that would stabilize the orbits within the existing framework. He said, essentially, classical physics is wrong here. It simply doesn't apply. And then he wrote down new rules. In 1913, Bohr published 3 papers, sometimes called the Great Trilogy, that laid out what we now call the Bohr model of the atom. The central ideas were these. First, electrons can only orbit the nucleus at certain specific allowed distances. Not any distance. Only particular ones. When an electron is in one of these allowed orbits, it does not radiate. Full stop. Not because some mechanism prevents it. Not because of some subtle cancellation. Because that is a rule of the quantum world. Electrons in allowed orbits simply do not lose energy by radiation. Second, the allowed orbits are the ones where certain quantity related to the electron's motion, specifically its angular momentum, is a whole number multiple of Planck's constant divided by twice pi. The angular momentum is quantized, just like energy. It can be 1 unit or 2 units or 3 units, but never 1.5. And finally, when an electron moves from one allowed orbit to another, it emits or absorbs a photon whose energy is exactly equal to the energy difference between the 2 orbits. Not approximately equal. Exactly. The electron doesn't slide gradually between orbits. It jumps discontinuously, and in doing so it releases or absorbs a single photon of precisely determined energy, precisely determined frequency, precisely determined color. Now, why did those particular orbits matter? Because there was a mountain of unexplained data sitting right in front of everyone. When you heat a gas, hydrogen say, and look at the light it emits through a prism, you don't see a smooth rainbow. You see sharp, bright lines at specific wavelengths, with darkness everywhere else. Each element has its own unique pattern of lines. Hydrogen's pattern is different from helium's, which is different from sodium's, which is different from every other element. These spectral lines had been observed and catalogued since the mid-19th century. In 1885, a Swiss school teacher named Johann Balmer had found a simple formula that predicted the wavelengths of hydrogen's visible spectral lines with remarkable precision. But nobody knew why the formula worked. It was a numerical pattern without an explanation. When Bohr calculated the energy levels of his allowed orbits for hydrogen and then worked out the frequencies of photons that would be emitted when electrons jumped between those levels, the numbers matched Balmer's formula precisely. Not approximately. Not roughly. With stunning quantitative agreement. The lines of the hydrogen spectrum fell out naturally from a model built on the simple postulate that electrons could only occupy certain orbits and jumped between them by emitting or absorbing photons. Einstein, on hearing the result, reportedly said that this was one of the greatest discoveries. Rutherford was impressed but genuinely troubled. He wrote to Bohr asking how the electron decided which orbit to jump to and when. It was a penetrating question, and Bohr didn't have a real answer. The model worked. The mechanism behind it remained mysterious. And the model had limits. It worked beautifully for hydrogen, with its single electron. When physicists tried to apply it to helium, with 2 electrons, or to any more complex atom, the predictions started failing. It was like having a master key that opens one specific lock and nothing else. Something more general was needed. Something that could handle not just hydrogen but the entire periodic table. A true mechanics for the atomic world. That deeper framework would take another decade to emerge, and it would come from a remarkable generation of young physicists working with extraordinary intensity in the middle of the 1920s. But before we get there, one more crucial idea had to arrive. An idea so strange that even the physicist who proposed it wasn't sure he believed it. It came from a French aristocrat with a physics degree and a very unusual question. Louis de Broglie, pronounced roughly de Broglie, came from a family with centuries of history in French military and political affairs. He held the title of prince. He had initially studied history at the Sorbonne, heading toward a career in the humanities, but conversations with his older brother Maurice, a physicist working on X-rays, had pulled him towards science. By 1923, he was working on his doctoral thesis, and the question that kept recurring to him was this. Einstein had shown that light, which everyone treated as a wave, also behaves like a particle, the photon. So shouldn't the reverse also be true? Shouldn't matter, which everyone treated as particles, also have a wave nature? He wasn't speaking loosely or metaphorically. He meant it precisely. An electron, a tiny speck of matter with definite mass and definite electric charge, something that leaves tracks in cloud chambers and can be deflected by a magnetic field. That thing also has a wavelength. Also ripples, also diffracts and interferes, just like light passing through Young's double slit. And he wrote down a formula. The wavelength of any particle equals Planck's constant divided by the particle's momentum. Lambda equals h over p simple, clean, and containing, as always, Planck's constant in the numerator, connecting this radical new idea back to Planck's reluctant invention of 23 years earlier. Notice what this formula says about everyday objects. A baseball has a large mass and therefore large momentum even at moderate speed. Divide Planck's absurdly tiny number by that large momentum and you get a wavelength so absurdly small that no instrument could ever detect it. That's why baseballs don't diffract around corners. The wave nature is there in principle but completely invisible in practice. But for something as light as an electron, the formula gives a wavelength on the order of the size of an atom. And at that scale, the wave nature is not invisible. It's dominant. It's everything. De Broglie's thesis committee wasn't sure what to make of it. The idea was elegant and it had mathematical support, but claiming that electrons were waves seemed like the kind of thing that required more than elegance. One of the examiners sent the thesis to Einstein for second opinion. Einstein replied that de Broglie had lifted a corner of the great veil. That was sufficient. The thesis was approved. De Broglie won the Nobel Prize in Physics for it in 1929. And 4 years after his thesis, the experimental confirmation arrived. In 1927, Clinton Davison and Lester Germer at Bell Labs in New Jersey were firing electrons at a nickel crystal and observed a diffraction pattern. The electrons were behaving exactly like waves, scattering off the regularly spaced planes of atoms in the crystal the same way X-rays scatter off crystal planes. Independently, George Paget Thomson, son of J.J. Thomson who had discovered the electron as a particle, demonstrated electron diffraction through thin metal films. Father discovers the electron is a particle. Son shows it's a wave. Both won Nobel Prizes. Both were right. The universe genuinely insists on both descriptions. De Broglie's idea also did something elegant that Bohr's model had left unexplained. Bohr had said that electrons could only occupy certain orbits, the ones where the angular momentum was a whole number multiple of the reduced Planck's constant. He had postulated this rule without explaining it. De Broglie's wave picture provided the explanation. If an electron is a wave traveling around the nucleus in a circular orbit, that wave must close in on itself after one complete orbit. It must fit. The way a guitar string can only vibrate at frequencies where a whole number of half wavelengths fit between the fixed endpoints. If the electron wave doesn't complete a whole number of wavelengths in one orbit, it interferes destructively with itself and that orbit cannot exist. The only stable orbits are the ones where the wave fits perfectly. And when you work through the mathematics, those are precisely the orbits Bohr had postulated. The quantization of angular momentum isn't a mysterious rule handed down from somewhere. It's a natural consequence of electrons being waves. The same reason a flute plays only certain notes. By the mid-1920s, the pieces were accumulating. Energy is quantized. Light is both wave and particle. Electrons are both wave and particle. Bohr's model works for hydrogen but breaks down for anything more complex. There's this growing feeling in the physics community that what's needed isn't another patch, another ad hoc rule to add to the patchwork. What's needed is a completely new mechanics, a new framework for describing the behavior of things at the atomic scale that would replace Newton's laws the way Einstein's relativity had replaced them at high speeds. And in 1925 and 1926, that framework arrived almost simultaneously from two completely different directions, two completely different people, in two completely different styles. The first came from Werner Heisenberg. In the summer of 1925, Heisenberg was 23 years old, working as an assistant to Max Born in Göttingen. He was brilliant, impatient, restless, and he was suffering terribly from hay fever. The pollen in Göttingen that summer was so bad that he could barely function. So he asked Born for leave and took a ferry to Helgoland, a small rocky island in the North Sea with almost no vegetation and, crucially, almost no pollen. And alone on that windswept island, recovering from his allergies and sleeping very little, he worked through something radical. Heisenberg's approach was built around a single austere principle. Discard everything you cannot observe. You cannot see an electron traveling around a nucleus. You cannot measure its position as it moves through its orbit. What you can observe are the frequencies and intensities of the light that atoms emit and absorb, the spectral lines. So build a theory entirely from those observable quantities. Nothing else. Heisenberg constructed arrays of numbers, tables encoding the frequencies and intensities of all possible transitions between energy states. He worked out rules for combining these tables, for calculating the behavior of a quantum system without ever invoking an electron's position or trajectory. The mathematics he ended up with was strange. When he multiplied two of his arrays together, the result depended on the order of multiplication. If he called his quantities A and B, then at times B was not the same as B times A. In ordinary arithmetic, the order never matters. 3 times 5 is the same as 5 times 3. But Heisenberg's quantities violated this. He found it deeply unsettling. He later said he was so disturbed by this non-commutativity that he spent most of one night checking and rechecking his calculation. At 3 in the morning, when he had confirmed it beyond doubt, he was too excited to sleep. He walked out to the tip of the island and watched the sunrise over the water. When he returned to Göttingen and showed his work to Max Born, Born looked at the arrays of numbers and recognized the mathematical structure immediately. Heisenberg had reinvented matrix algebra, a branch of mathematics that had been developed in the 19th century and that described, among other things, arrays of numbers whose multiplication is order-dependent. Born, along with his student Pascual Jordan, helped Heisenberg formalize the theory into what became known as matrix mechanics. It was the first complete, self-consistent formulation of quantum mechanics. It worked. It predicted the spectral lines of hydrogen correctly, and when applied to more complex atoms, it gave right answers where Bohr's model had failed. But it was also profoundly abstract. There was no picture of what was happening. No visualization. No electron somewhere doing something. Just these abstract arrays of numbers obeying algebraic rules that seemed to have no intuitive physical content. Most physicists found it very difficult to work with and nearly impossible to understand at any intuitive level. Then, just a few months later, in early 1926, a completely different formulation arrived from an Austrian physicist named Erwin Schrödinger. Schrödinger was in his late 30s, considerably older than most of the other quantum revolutionaries. He was directly inspired by de Broglie's matter wave idea. If electrons are waves, Schrödinger reasoned, then there must be a wave equation that governs them, a differential equation describing how the wave evolves in space and time. Just as Maxwell's equations govern electromagnetic waves. Just as the classical wave equation governs vibrations on a string. He set out to find that equation. The discovery has become one of the more legendary moments in the history of science, and perhaps the most colorful in terms of the surrounding circumstances. In December 1925, Schrödinger went on holiday to a villa in Arosa in the Swiss Alps. He brought with him a woman whose identity has never been conclusively established. And over the course of a few weeks of intense work during that alpine retreat, he derived the equation that bears his name. The Schrödinger equation describes the evolution of a mathematical quantity called the wave function, usually written with the Greek letter psi. The wave function is associated with a quantum system, an electron or a set of electrons or any quantum object, and it evolves in a deterministic, smooth, continuous way according to Schrödinger's equation. In that sense, it's completely classical. It's the kind of differential equation that physicists had been using for centuries. You can picture the wave function as a wave rippling through space, spreading out, interfering with itself, diffracting around obstacles. And crucially, it gave physicists something to visualize. After the arid abstraction of matrix mechanics, Schrödinger's wave equation felt like a return to something physically intuitive. Physicists embraced it. It was more familiar, more tractable, more amenable to calculation. And it gave exactly the same predictions as Heisenberg's matrix mechanics for every problem anyone tried. Schrödinger himself showed in 1926 that the two formulations were mathematically equivalent. Two completely different approaches, one from an abstract algebraic principle, one from a physical analogy with wave motion, had arrived at exactly the same place. Later, Paul Dirac would unify both into a more general mathematical framework that was elegant enough to make physicists actually sigh with pleasure. But the more pressing question was one the mathematics couldn't settle by itself. What does the wave function actually mean? Schrödinger believed, at least initially, that the wave function was a literal physical wave. That the electron really was spread out through space in the shape described by the wave function. He thought he had found the electron's true nature. It wasn't a particle at all. It was a wave, like a ripple on a pond, spread out and continuous and perfectly described by his equation. But Max Born looked at this interpretation and found a serious problem. When you actually measure where an electron is, you always find it in one specific place. Not smeared out. Not distributed. One place. So the wave function can't literally be the electron, because the electron always shows up as a point. Born proposed something more subtle and far more disturbing. He said the wave function is not the electron. It's a probability wave. Specifically, the square of the wave function at any point in space gives the probability of finding the electron at that point if you make a measurement. Before measurement, the electron doesn't have a definite position. It has a probability distribution. The wave function tells you the probability of each possible outcome. When you make a measurement, you get one specific result, and after that measurement the wave function changes, collapses, to reflect the new state of knowledge. Before measurement, a spread-out probability cloud. After measurement, a definite value. This is Born's rule, and it is one of the cornerstones of quantum mechanics. It says, at the most fundamental level we have yet discovered, nature is probabilistic. Not because we're ignorant of the underlying details. Not because our instruments are imprecise. But inherently, irreducibly, at the level of individual quantum events, outcomes are random. The wave function gives you probabilities and nothing more. There is no deeper layer, no hidden machinery that predetermines which outcome you'll get. The universe is not a clockwork. At its deepest level it rolls dice. And this is where a fault line opened in 20th century physics that has never fully healed. Niels Bohr, by the late 1920s, had become the dominant interpretive voice in quantum mechanics. He was based in Copenhagen, where his institute had become the world's most important center for theoretical physics. He had thought about the foundations of the theory more deeply than almost anyone. And his interpretation, which became known as the Copenhagen interpretation, embraced what most physicists found deeply uncomfortable. Bohr said that quantum mechanics is complete as it stands. The wave function is the most complete description of a quantum system that is possible. There is no deeper reality to access. Questions about where the electron was before you measured it do not have answers. The electron didn't have a position before the measurement. The measurement doesn't reveal a pre-existing property. It creates the property. Reality at the quantum level is not determined until it is observed. The act of measurement is not a passive recording of something that already exists. It is an active creation of what exists. The uncertainty principle, derived by Heisenberg in 1927, fit naturally into this picture. Heisenberg showed, using a beautiful mathematical argument built on the non-commutativity of Bohr's quantum variables, that certain pairs of physical properties cannot both be precisely defined simultaneously. Position and momentum are the famous example. If you know a particle's position very precisely, its momentum is necessarily very uncertain. If you know its momentum precisely, its position is smeed out. The more precisely you pin down one, the more uncertain the other becomes. And this is not a statement about the limits of measurement technology. It's not saying that our instruments are too clumsy and disturb the particle when they measure it. The uncertainty is fundamental. It's built into the mathematical structure of the theory. Position and momentum are not two things that a particle has simultaneously and that we fail to measure accurately. They are not both well-defined at the same time. The particle doesn't have a precise position and a precise momentum at the same time. Reality itself is fuzzy at that scale. Bohr folded this into a broader philosophical principle he called complementarity. The idea that quantum objects have complementary aspects, wave and particle, position and momentum, that cannot both be fully present at once. Ask a wave question and you get a wave answer. Ask a particle question and you get a particle answer. But you cannot ask both simultaneously, and you cannot ask what the electron really is when you're not asking either. The question doesn't have a factual answer in the quantum world. Bohr insisted on this with a philosophical intensity that some of his colleagues found almost mystical. Not everyone was comfortable with this. Not even close. The person who objected most clearly, most eloquently, and most persistently was the same man who had started the quantum revolution with his photoelectric paper. Einstein had deep, principled, carefully thought-out objections to the Copenhagen interpretation. He believed that particles have definite properties whether or not anyone is measuring them. He believed that a complete theory of physics should, in principle, allow you to predict the outcome of any measurement with certainty, not just with probability. He believed the universe was not fundamentally random. He did not believe God plays dice. That phrase is the most famous summary of his position, and while it's been simplified in the retelling, it captures something real about what he believed. And the debate between Einstein and Bohr over the meaning of quantum mechanics became one of the most celebrated intellectual confrontations in the history of science. It played out most dramatically at a series of physics conferences in Brussels, funded by the Belgian industrialist Ernest Solvay, over the late 1920s and early 1930s. These were invitation-only gatherings of the world's top physicists, and the photograph from the 1927 Solvay conference show a room containing Einstein, Bohr, Heisenberg, Schrödinger, Dirac, Born, Pauli, de Broglie, Lorentz, Marie Curie, and about 15 others. 17 of the 29 people in that room were or would become Nobel laureates. It is very plausibly the most intellectually extraordinary group photograph in human history. At these conferences, Einstein's strategy was not to dispute the mathematics of quantum mechanics. He knew the mathematics worked. His approach was to construct thought experiments, carefully designed hypothetical scenarios that purported to show contradictions in the theory, or to show that it was incomplete, that there must be a deeper deterministic reality hiding underneath the probabilistic surface. Each morning at breakfast, Einstein would present Bohr with a new thought experiment. And each day Bohr would agonize over it, pace and mutter and work through the logic, and by dinner he would have found the flaw. The debates were genuine, rigorous, and conducted with great mutual respect despite the depth of disagreement. Any of the most famous of these exchanges came at the 1930 Solvay conference. Einstein proposed a thought experiment involving a box full of radiation with a clock-controlled shutter. The idea was that by opening the shutter for a precisely known interval, letting out a single photon, and then weighing the box before and after using his own equation E equals mc squared to determine the photon's energy from the change in mass, you could know both the precise timing and precise energy of the photon. That would violate the time-energy version of the uncertainty principle. This was a beautiful, well-crafted trap, and it genuinely rattled Bohr. Reportedly, Bohr was distressed that evening, unable to immediately see the escape. But by the next morning he had found it, and the escape route used Einstein's own general theory of relativity. The act of weighing the box, Bohr pointed out, causes it to move slightly in the gravitational field. And general relativity says that a clock moving in a gravitational field experiences gravitational time dilation. That small displacement introduces an irreducible uncertainty in the timing of the shutter, an uncertainty that, when you walk through the calculation carefully, is exactly sufficient to preserve Heisenberg's principle. Einstein had been defeated by his own theory. Einstein never successfully found a logical contradiction in quantum mechanics. But he kept trying, and by the 1930s he had changed tactics. Instead of trying to show the theory was logically inconsistent, he tried to show it was incomplete. That there were real physical states of affairs it failed to describe. And this led to one of the most consequential papers in the history of physics. In 1935, Einstein published a paper with Boris Podolsky and Nathan Rosen. It is universally known by their initials, EPR. The title asked a deceptively quiet question: can quantum mechanical description of physical reality be considered complete? Their argument went like this. Imagine a physical process that produces two particles flying off in opposite directions with their properties correlated. Quantum mechanics predicts that if you measure a certain property of one particle and get a certain result, the corresponding property of the other particle will be found in a correlated state, even if the particles are far apart, in principle on opposite sides of the galaxy. But according to Copenhagen, neither particle has a definite value for this property before measurement. The act of measuring one particle determines its value, and simultaneously the value of the other particle, regardless of the distance between them. Einstein found this conclusion unacceptable. Measuring particle A couldn't instantaneously affect particle B on the other side of the galaxy. That would require some influence traveling faster than light, in violation of special relativity. Einstein called it spooky action at a distance. The simpler and more sensible conclusion, he argued, was that both particles carried definite correlated properties all along, from the moment they were created. Like a pair of gloves separated into two boxes. When you open your box and find a left glove, you instantly know the other box contains a right glove. Not because of any spooky action, because they were always left and right. You just didn't know which was which. The quantum mechanical description, which assigns probabilities rather than definite values, simply doesn't capture this pre-existing reality. It's incomplete. There are hidden variables, definite pre-existing properties that quantum mechanics doesn't describe, and a complete theory would include them. This argument was serious. It was carefully constructed. It was based on principles, locality, the idea that influences can't travel faster than light, and realism, the idea that physical properties exist independently of measurement, that most physicists considered non-negotiable. Bohr's response, published later that year, was acknowledged even by people sympathetic to Copenhagen as somewhat convoluted and less than fully satisfying. The EPR argument was a genuine challenge, and it lingered unresolved. It lingered for almost 30 years. Most working physicists during that time simply set the interpretive debate to one side and got on with using quantum mechanics to predict things and build things. The interpretation was seen as a matter of philosophical taste that didn't affect calculations. You could be a Copenhagen person or agree with Einstein about hidden variables, and your calculations would be identical either way. The equations didn't care which camp you were in. And then in 1964, an Irish physicist named John Stuart Bell, working at CERN in Geneva, did something that changed everything. He asked a question that sounds simple but that nobody had thought to formulate clearly. Is there actually an experimental difference between quantum mechanics and hidden variables theories? Can you do a test that gives different results depending on which view is correct? Bell discovered that the answer is yes. He derived a mathematical inequality, now called Bell's inequality, that any local hidden variables theory must satisfy. The word local here is crucial. It means theories in which the properties of a particle are determined by information that travels no faster than light, which is what Einstein had required. Bell showed that if the universe really works the way Einstein hoped, if particles carry definite pre-existing properties and there are no faster-than-light influences, then certain statistical correlations between measurements on distant entangled particles are bounded. They can't exceed a certain maximum value. But quantum mechanics predicts that in carefully designed experiments, those correlations exceed that maximum. The difference isn't subtle. It's a clean, measurable experimental distinction. This had moved the debate from philosophy to physics. The tests began in the 1970s. The most celebrated early experiments were conducted by Alain Aspect and his colleagues at the University of Paris-Sud-Nancy in 1981 and 1982. Aspect used pairs of photons produced by excited calcium atoms, entangled so that their polarizations were correlated. He measured their polarizations along different angles and accumulated statistics. Crucially, His experiment included rapidly switching the measurement angles while the photons were already traveling, so that no signal traveling at or below the speed of light could pass from one detector to the other before the measurements were made. The results were unambiguous. Bell's inequality was violated. The correlations were exactly what quantum mechanics predicted, and they exceeded what any local hidden variables theory could possibly produce. The conclusion is stark. If you want to believe in hidden variables, if you want particles to have pre-existing properties that quantum mechanics simply doesn't describe, you have to give up locality. You have to allow for instantaneous influences that travel faster than light, which conflicts with special relativity. Einstein's entire argument rested on both locality and realism. Bell and Aspect showed you cannot have both. One has to go. Experiments have only gotten more rigorous since Aspects. In 2015, Ronald Hansen's team at Delft University performed what physicists consider the first truly loophole-free Bell test, closing every major experimental escape hatch simultaneously. The result was the same. Nature is as strange as quantum mechanics says it is. Einstein's hope that the world is fundamentally sensible, that things have definite properties whether or not anyone looks at them, and that influences can't travel faster than light, has been experimentally ruled out. You can keep one of those properties but not both. Einstein died in 1955, 9 years before Bell published his theorem and decades before the experiments. He never saw the question he had so carefully posed answered so definitively. And the universe answered in Bohr's favor, at least in the sense that local hidden variables are ruled out. There's something genuinely poignant about that. The man who started the quantum revolution, who saw further and more clearly than almost anyone into the structure of nature, spent the last decades of his intellectual life in a campaign against the implications of a theory he had helped create. And he was wrong. The universe is as strange as Copenhagen says. But let's not declare it too cleanly, because the story is more nuanced than that. Einstein may have been wrong about local hidden variables, but the questions he raised about entanglement turned out to be extraordinarily fruitful. Entanglement isn't a curiosity to be dismissed. It's a resource. It's the physical foundation of quantum computing, quantum cryptography, and quantum teleportation. The very phenomenon Einstein called spooky action at a distance has become one of the most actively exploited effects in modern physics and engineering. So in a strange way, Einstein's most famous objection to quantum mechanics pointed towards some of its most powerful applications. Now let's change the scale and talk about what quantum mechanics says when you apply it not to individual particles in isolation but to enormous collections of particles packed together into solid materials. Because this is where quantum physics stopped being a debate between extraordinary people in Brussels and became the reason you have a smartphone in your pocket and the modern world runs on electricity in ways it couldn't have run 50 years ago. Let's start with a question that sounds like it should have a simple answer. A copper wire conducts electricity. A rubber band does not. Why? You might say, loosely, that copper has free electrons and rubber doesn't. That's true as far as it goes. But it doesn't explain anything. Why are copper's electrons free? What is it about the atomic structure of copper versus rubber that makes one a conductor and the other an insulator? Classical physics can describe the difference but can't explain it from first principles. Quantum mechanics can. The explanation comes from something called band theory, and it rests on a principle we haven't talked about yet. One of the most important principles in quantum mechanics, and one of the least known outside physics. It's called the Pauli exclusion principle, and it was proposed in 1925 by Wolfgang Pauli. Pauli is one of those figures who looms very large in the history of physics, partly for his contributions and partly for his personality. He was genuinely one of the sharpest theoretical physicists of the 20th century, with a gift for mathematical insight that his contemporaries found almost supernatural. He was also ruthlessly critical. There is a story, probably embellished but revealing in its persistence, that Pauli once dismissed a colleague's work by saying it was not even wrong. The implication being that the work was so confused it didn't even rise to the level of making a false claim. It was simply meaningless. That was the kind of standard Pauli held people to, including himself. His supervisor and mentor Max Born was once helping Pauli with a calculation. Born made an error. Pauli corrected him immediately, then said, while continuing to write, that he supposed even Born had the right to be wrong occasionally. In 1925, Pauli was wrestling with a puzzle about how electrons arrange themselves in atoms. Bohr's model had energy levels that electrons could occupy. Why didn't all the electrons in an atom simply pile into the lowest energy level, the ground state? That would minimize the total energy, and classical systems tend to fall into their lowest energy configuration. But atoms demonstrably didn't work that way. The electrons in heavier atoms spread across multiple energy levels in specific, systematic patterns that gave each element its unique chemical properties. Something was preventing the electrons from all crowding into the same low-energy state. Pauli's insight: no two electrons in an atom can occupy the same quantum state simultaneously. That's it. That is the exclusion principle. Electrons in an atom are characterized by a set of quantum numbers, values that describe their energy, orbital shape, orbital orientation, and a property called spin. Spin is an intrinsic angular momentum that electrons carry, and it can point in one of two directions, conventionally called up and down. Each combination of quantum numbers defines a unique quantum state, and each state can hold at most one electron. Two electrons in an atom cannot have identical sets of quantum numbers. If one electron is occupying a state, all others are excluded from it. This forces electrons to stack upward into higher and higher energy states. The first available state fills. The second electron goes into the next available state, and so on upward through the energy levels. It's like a building where each apartment can only hold one occupant, and the elevators only go up. Each new tenant has to take the next available apartment above the last occupied one. The chemical properties of an element, how reactive it is, what kinds of bonds it forms, whether it's a metal or non-metal, all of that reflects how many electrons are in the outermost occupied energy level and what orbitals they are in. The entire periodic table is a consequence of Pauli's exclusion principle and the quantum mechanical energy levels of atoms. The whole of chemistry follows from this one rule. Now think about what happens when you bring a huge number of atoms together, close enough that their electron clouds interact. Instead of isolated atoms with sharp discrete energy levels, you get what are called energy bands. The reason is subtle, but the intuition is this. When two atoms approach each other closely enough that their wave functions overlap, the energy levels of one atom interact with those of the other. Take a crystal of silicon. Quantum mechanically, each silicon atom has the same energy interactions, and they forms four covalent bonds. Instead of two states both at energy regular lattice, you get one state at energy slightly above E and one at energy slightly below. One silicon atom now bring together not two atoms, but 10 to the 23rd. Phosphorus has 5 outer energy level of every isolated atom to the lattice to the collective forming system. 4 bonds, and instead of sharp discrete levels, but that fifth electron has no bond to fill. It's loosely bound, and at room temperature it breaks free and becomes a mobile charge carrier in the conduction band. You've created an excess of negative charge carriers. This is an N-type semiconductor, N for negative. Now do the reverse. Replace a silicon atom with a boron atom. Boron has only 3 outer electrons. It forms 3 bonds but can't fill the 4th. There's a hole, a missing electron, in the bond structure. And that hole behaves as a positive charge carrier. Neighboring electrons shift around to fill holes, effectively moving the hole through the lattice, like the empty space in a sliding tile puzzle. This is a P-type semiconductor, P for positive. And here is the essential trick that made the modern world. Put a piece of N-type semiconductor next to a piece of P-type and you create a PN junction. At that junction, Electrons from the N side diffuse across to fill holes on the P side. As they do, they leave behind positively charged phosphorus atoms on the N side and negatively charged boron atoms on the P side accumulate. This charge separation creates a built-in electric field at the junction that opposes further diffusion. An equilibrium is established with a thin depletion zone at the junction where no free carries exist. Apply a voltage in one direction and you reduce the built-in field, allowing current to flow easily. Apply it in the opposite direction and you reinforce the field, blocking current almost completely. You've built a diode, a device that allows current to flow in only one direction. That asymmetry is enormously useful. And more importantly, combine two junctions and you have a transistor, the device that became the foundation of all digital electronics. The transistor was born at Bell Labs in Murray Hill, New Jersey, in December 1947. The people responsible were William Shockley, John Bardeen, and Walter Brattain. Each was remarkable in different ways, and the personal dynamics between them were complicated enough to make the story considerably more interesting than a straightforward account of scientific progress. Shockley was the group leader. He was brilliant, driven, and absolutely convinced that semiconductors were the key to the future of electronics. He had been thinking about semiconductor amplifiers since before the Second World War. He had in mind a device that would use an electric field to control the flow of current through a semiconductor, essentially a voltage-controlled switch. He designed it. Brattain built it. It didn't work. No matter how they tried, the field had no effect on the current. Something was blocking it. It was Bardeen who identified the problem. Quietly, carefully, with the precision of a genuine theorist, he proposed that quantum mechanical surface states were the culprit. Electrons were becoming trapped at the surface of the semiconductor, forming a layer of charge that screened the external electric field before it could penetrate into the material. The field was being cancelled out at the surface itself before it could influence the bulk. It was a subtle quantum mechanical effect, and Bardeen nailed it. This was the kind of contribution that changes everything because it transformed a problem without a solution into a problem with a clear cause. ND therefore a path to a fix. Shockley received this insight somewhat badly. He had conceived the device. He had set the direction. And now Bardeen had identified why his design didn't work, which felt like a kind of correction he hadn't asked for. He began to withdraw from the day-to-day work. And so Bardeen and Brattain started working closely together, the two of them, exploring ways around the surface state problem. On December 16, 1947, Brattain made a device that worked. He had taken a small wedge of plastic, wrapped gold foil around it, and used a razor blade to cut a thin slit at the point of the wedge, creating two gold contacts separated by perhaps 50,000ths of an inch. He pressed this onto a small slab of germanium. When he applied a small signal to one gold contact, he could control a much larger current flowing through the other. Amplification. The device amplified the input signal by a factor of about 18. It was crude, almost toy-like in its construction. But it worked. Bardeen and Brattain had built the first transistor. Brattain's lab notebook entry from that day still exists. He recorded the results and noted the power gain. His supervisor signed the page as a witness. December 23, 1947. Everything after that moment traces back to that entry. When Shockley learned what Bardeen and Brattain had done without him, he was furious. Not because it failed, because it succeeded magnificently and he hadn't been in the room. His name was not on the patent for the point contact transistor. For a man of Shockley's ambitions, that was simply unacceptable. So over the New Year's holiday, nursing what seems to have been considerable wounded pride, he went off on his own and invented a different and ultimately better transistor. Instead of two contacts pressed against a surface, Shockley's design used a sandwich of semiconductor layers, N-type, then P-type, then N-type, or the reverse. By controlling the current flowing into the thin middle layer, the base, you could control a much larger current between the outer, more robust, more reliable, easier to manufacture. The junction transistor became the dominant architecture. All three men shared the 1956 Nobel Prize in Physics. By then they were barely speaking. Bardeen left Bell Labs for the University of Illinois, where he would go on to do foundational work on superconductivity and win a second Nobel Prize, the only physicist ever to win the prize twice in the same field. Brattain continued his research with characteristic modesty. Shockley moved to California, founding Shockley Semiconductor Laboratory in Mountain View in 1956, recruiting some of the brightest young engineers he could find. And then being so difficult to work with that 8 of them quit to found their own company. They became known as the Traitorous Eight, and the company they founded was Fairchild Semiconductor. 2 of those 8, Robert Noyce and Gordon Moore, later left Fairchild to start Intel. So the entire ecosystem of Silicon Valley, the venture capital culture, the startup culture, the geography of modern technology, traces back in a very real way to William Shockley being impossible to work for. History is genuinely strange. But the point is that every transistor ever built since 1947 is a quantum mechanical device. The band structure, the Pauli exclusion principle, the behavior of electrons in doped semiconductors, the formation of p-n junctions, the quantum mechanical tunneling that becomes both useful and problematic as devices shrink. All of it is quantum mechanics. The transistor is where the theory stopped being philosophy and became infrastructure. Once you have transistors, you can build logic gates. Circuits that perform simple logical operations on electrical signals representing ones and zeros. An AND gate outputs a 1 only when both inputs are 1. An OR gate outputs a 1 when either input is 1. A NOT gate flips the input. Combine these into larger circuits and you can add numbers, store information, compare values, make decisions. That's a computer. The first electronic computers in the 1940s used vacuum tubes as their switching elements, which were large, hot, fragile, power-hungry, and unreliable. A single vacuum tube could fail without warning and the machine would stop. A room-sized computer with 18,000 vacuum tubes failed constantly. Transistors changed this almost immediately. Smaller, cooler, faster, more reliable. And then came the integrated circuit, the idea of putting multiple transistors on a single piece of semiconductor, a chip. Jack Kilby at Texas Instruments and Robert Noyce at Fairchild arrived at this idea independently in 1958 and 1959. That's the moment modern electronics truly begins. Gordon Moore observed in 1965 that the number of transistors on a chip seemed to double roughly every 2 years. That empirical observation became known as Moore's Law, and it has held, with some variation, for nearly 6 decades. The processor in a contemporary smartphone contains somewhere around 15 billion transistors. 15 billion individual quantum mechanical switches, each one a p-n junction, each one doing what Bardeen and Brattain demonstrated with a wedge of plastic and a razor blade in 1947, but at a scale that would have seemed impossible to the people in that lab. And this relentless miniaturization has been running into quantum mechanics in new ways. When your transistor gate is only a few nanometers thick, meaning a few dozen atoms across. Errors. It's one of the fundamental reasons Moore's Law has slowed. We're not running out of engineering cleverness. We're running into physical limits set by quantum mechanics itself. The wave nature of electrons, the uncertainty principle, the probabilistic tunneling, these become obstacles rather than tools when the devices shrink past a certain threshold. And that collision with quantum mechanical limits is part of what has driven interest in a completely different kind of computing. One that doesn't fight quantum mechanics but uses it. The idea of a quantum computer has roots in the early 1980s. In 1981, Richard Feynman gave a talk at MIT in which he observed something that seems obvious in retrospect but that nobody had clearly articulated before. Simulating quantum systems on a classical computer is inherently inefficient because the number of states in a quantum system grows exponentially with its size. To simulate a quantum system of 50 particles on a classical computer, you'd need to track 2 to the 50th power possible states simultaneously. That's more than a quadrillion states. For 100 particles, it becomes completely impossible for any classical machine that could ever be built. Feynman's insight, a computer that is itself quantum mechanical, could simulate quantum systems naturally, because it is one. It would be exponentially more efficient.